So we've all seen this movie, right? Honey, I Shrunk the Kids. A well-meaning, slightly chaotic scientist accidentally shrinks his kids. In the world of engineering, we are these scientists. A lot of the time, we're accidentally, blowing up the bill instead of shrinking it. So today, we're going to flip that script. We're going to go become that hero that shrinks the bill. So when you think about it, most of the time, bill shocks are very common in the industry. Sometimes you'll see someone spending, $10K on just a 22-second query. Sometimes you'll have devs querying the whole data lake that runs for 2-3 weeks, ends up spending 75 grand. And one of these classics, the customer does training in Cosmo DB, leaves the instances running, and later gets a call from Microsoft because they just spent 45 grand on it. So all this powerfully illustrates a critical truth for us, which is cloud comes with convenience, and convenience comes at a cost if you're not careful about the compute that you're consuming. So a lot of this shift has happened from traditional fixed IT costs to consumption-based models in cloud, inherent complexity that you get with dynamic pricing, the rapid evolution of services, and the decentralized sort of consumption pattern across your teams, right? So preventing these bill shocks, this is precisely what we're here for. Before we get started, something about the speaker, it's Harjot, staff software ML eng at Intuit. So primarily looking at generative AI. I'm going to talking about myself in third person, but yeah. So I've been fortunate enough to work in the domain which has large data-intensive, volume-intensive applications where you're processing terabyte-scale data and billions of emails, text, images, where small changes can have a major cascading effect over your cost. So what I wanted to do was share my journey and my learnings. But before we get started, huge thanks to the lead dev organization. It takes months of effort to get here. So let's get started. So the way we're going to approach this is we're going to have a two-stop journey. The first stop is the OpEx and the audit framework. We're going to talk about the foundation of running a well-oiled machine. Then we're going to talk about some common patterns. Some patterns that can reveal high costs that have helped me save hundreds of thousands of dollars of operational costs over the years. And so let's get started. The first stop, again, the framework itself. What we want to talk about is a framework called Minimum Audit Framework. This is a term I came up with. Think of it as a trustee roadmap for complex cloud costs. So this isn't just about cutting costs. We're looking at building a sustainable operational excellence. So we'll break it down into 3 steps, which is pre-audit, things you set up for your audits, Then you look at the audit itself, which is digging into the nitty-gritty of things. And finally, the post-audit itself, right? Where it's all about making sure your hard-earned savings stick around and they grow. So let's look at the first pre-audit phase, which is about preparing the environment people for success. So the step involves 2 main critical parts, which is technical setup and the cultural setup. So when you talk about the technical setup, the first line of defense for you is always the cloud provider setup, right? We're talking about the AWS Cloud Explorer, GCP billing, Azure cost management. So these are your first line of defense, and these aren't just fancy charts, right? So you're looking for budgeting, certain critical features like budgeting, forecasting, anomaly detection, and you need to combine these with some best practices around, you need to understand your consumption patterns, set up your tiered budgets. So not only having alerts around, say, 100% of the cost consumption, start it tiered at, say, 60%, 70%, so that before you hit the last sort of, 100% of your budget, you're intimated by alerts. And also establish some centralized governance that helps you, streamline your process. Next, in the technical setup, we're talking about microservices. We're talking about the holy trinity here. So the metrics, logging, tracing. So make sure you have the toolings like Prometheus, Grafana for metrics, Jaeger for tracing, and ELK stack for your logs. So these are your eyes and ears. The traffic spikes cost a fortune, so make sure you have visibility around these. Next thing, one of the big contributors towards cost is data platform and data engineering. Huge cost comes from volume of data and the compute required to process these, right? So observability is huge for us. So this involves monitoring your storage, ensuring your compute clusters are right-sized, and make sure you explore other platforms like for data profiling, such as Soda, Monte Carlo. And what these platforms do is they give you accessibility to quality checks, data quality checks, and data distribution checks, and which often uncover surprising opportunities for savings. Think about significant cost downstream if you have upstream changes. Next, in the setup itself, you're talking about cultural. So moving beyond the bits and bytes, we're talking about the cultural setup, which is often overlooked. Again, you can have fancy dashboards, but if your engineering culture isn't aligned with cost consciousness, you'll be swimming upstream. So think about cost optimization as everyone's business, not just finances. We're going to look at two key frameworks here, like enabling your engineers. So one of the big things you need to do is enable your engineers, give them access because they are the front line. They are the ones who are writing the code, spinning up the resources, making architectural decisions that directly impact you. So give them visibility, of course. Don't hide it behind, say, a finance portal that takes you 5 different Jira tickets to get access to. Put them in a dashboard, integrate it. So this ensures the collaboration and cost optimization is a shared objective, right? It's not seen as a burden. And the next thing is, within the culture, you have to really incentivize and recognize good efforts towards cost saving. So what that means is not holding off to bonuses towards the end of the year, right? Make sure you have some sort of setup for spot bonuses, something tangible, right? It could be as minimal as giving out gift cards for something that you've done over the week, right? So make sure align incentives with your company goals. So Charlie Munger rightly said, show me the incentive, I'll show you the outcome. So we get the behavior, we reward. So make sure you have this incentive super response going. Next thing, we've reached the first phase, which is pre-audit. We go into the audit phase, which is about regularly scheduling or scrutinizing your systems, finding inefficiencies, and savings, right? This isn't about a once-and-done thing. You're going to commit to it, and you're going to do it on a regular basis. And the way we're going to approach this is we have 3 things in there. One is the OpEx review. Next is the monthly housekeeping. And the third one is like a fun little bounty program thing. So when you talk about OpEx reviews, make it a weekly thing or a bi-weekly thing. Meet with your operational expenditures, sort of teams that are involved in it. Involve your engineering leads, product managers, finance partners. Review your cost reports. Find certain patterns that you can brainstorm on. And foster the shared ownership within the cloud build architecture. Next thing is monthly housekeeping. This is huge. Again, something that you can explore with your organization is toward the end of the month, say on a Wednesday afternoon, you can schedule a housekeeping session. What this does is it makes these engineers go and find unattached storages, terminate idle instances, review your old cloud logs, so that you can find efficiencies within your regular work. Next up, we have a fun little engagement around bounties, create dashboards where engineers can come in and check what's happening. And these kind of dashboards can give them insights around what's the most cost-consuming aspect of your work and involve other teams as well.
If you're enjoying this, then Lead Dev's got loads more to offer and there's tons to explore.
So the reason I love Lead Dev so much is they've got such a range of content on so many different topics in the world of engineering, leadership, and management.
So Lead Dev helped a lot on building my own career, right? And it's great to also see how it's helping the new generation as well.
Make sure to sign up and join us at leaddev.com.
We reach the end of the sort of audit phase. Now we go to the post-audit phase. And this is how you enable, basically, implement policies that refine the stuff that you found in the audit, right? So the first stage would be diagramming and optimization. So think about visualizing your system, right? So some of the things that are not always obvious in hindsight come up when you start visualizing things. So optimization points like redundant components, overly complex data parts, you can find these through diagramming. And once you've found those, you can start optimizing them. What that means is you can start optimizing for right-sizing your compute, fine-tuning your database queries, and re-architecting some part of your data pipelines that are consuming a lot of compute. The next step in the post-audit phase would be a blameless education and record-keeping process. So make sure you foster a continuous improvement process, share your knowledge, document everything. and techniques, right? And build a valuable knowledge base that you can further pass on to new joinees as a learning step. And lastly, in the post-audit phase, look at automation. So you're looking at opportunities to save, shut down, automate instances, right? Use scripts for environment shutdowns, right? Why wait for the whole sort of environment to shut down by itself, right? Implement life cycles for data cleanup, right? Don't put manual efforts in cleaning up your sort of storage, things like that. So we've come to the end of the framework, which is pretty straightforward. You set up, you run your audits, grow your savings, make it a repetitive process. And with that, we've reached the second stop in the path, right? So the common patterns. So the thing that happens is once you start applying this framework, going through several iterations of this, you'll start seeing some repeat pattern and overages, and these will emerge organically, right? And what you need to make sure is you're building a mental model around this. You're trying to figure out what are your obvious costs and certain hidden costs that you'll discover as you do these, right? And to illustrate this, what we're going to do is we're going to look at let's call it a white label ML pipeline. It's a standard configuration where you start up with your raw data, you process it, you refine it, you get it to a point where it becomes features for your models. And then you try to optimize on the compute, and you start to sort of leverage external APIs, you start to use GPUs to further enhance your data and ML predictions, right? Pretty standard stuff. But when you look at it, you'll find there are some common suspects, right? These are some of the things that I've noticed over the years. And these common suspects tend to be the data prep layer, right? And then you have the distributed compute. And then you have the GPU, which is huge nowadays. And then you have some external APIs. And sometimes you least expect, and they tend to be the most notorious, they can be the logs in the network aspect of things, right? So let's start with the first suspect, right? The first suspect, the data preparation, right? When you think about it, they have some common patterns of operation, and they can be really lethal towards your cost. So one of the most common patterns in your data layer or data preparation is excessive data scans. Think about it, the select stars, right? Consider you're using BigQuery. I love BigQuery, again, nothing against it. But yeah, so you can leverage BigQuery to run massive workloads. But the thing is, there are some pitfalls, right? Consider this database, which is massive, 800 terabytes of data, and you just want to prune it and scan it and just quickly check certain records, so you put a limit clause. What that does is you just spend $4,000 in one single run, right? And imagine some dev running this query and later finding out how much cost it's got. So the things you can do to prevent this is start clustering and partitioning your tables, right? So that'll enhance your searchability of data, as well as limit the amount of data that you scan every time. So you would put a partition clause when you're creating the table, and that should do it. Now, so the thing is, even though you have partitioning, you have to enforce these rules, right? So you have to spend a good amount of time to ensure that everyone's adhering to it. So the way to do that is you require the partitioning clause every time you query this, right? So the other things I can do, especially with BigQuery, is start digging into for more insights, right? What that means is looking at execution graphs. These give you extensive amount of information about the data flow, the data that you're capturing at every step, the amount of bytes you're shuffling across different nodes. And once you find patterns over here, you can start optimizing and reducing those queries into separate tables that can be used further for analysis. The other big thing is job views. Not a lot of folks investigate this, but if you look at the information schema and the jobs in BigQuery, what it gives you is extensive information about each query and the amount of data it's querying, the number of slots used, the bytes processed. So what this does is it gives you a granular amount of data that you can build your dashboards on. Remember we talked about gamifying your cost optimization with those bounty hunts? You can leverage these data sources to build those dashboards wherein you can show the most expensive queries and have it be accessible to everyone in your ecosystem. And what that does is it brings in collaboration, right? You can have other teams looking at the same query, giving you, another perspective about how to optimize these things. So really leverage job views. It's crucial for your cost management, performance analysis, right, and auditing as well. There are certain other remedies that you can do to really shrink that cost. Certain best practices around data engineering, reduce the data before joins, right? Choose the appropriate pricing model. This is another key one because what ends up happening is people don't understand the on-demand pricing versus the reserve pricing. So understand what's actually needed for you. Next thing, avoid frequent table overrides. So this is crucial for moving your data to a lower tier system. Next, use query quotas. Enforce query quotas at user level so that you don't exceed your regular billing with $4,000 queries every time. Next suspect, the distributed compute. The common patterns you'll see over here tend to be mostly staggered tasks, right? What we mean by staggered tasks is in distributed environment, your processing gets distributed across different nodes. And you'll find sometimes this one particular section of your data processing gets staggered, right? What that means is this one node takes forever to compute whatever task it's been given, and that stage is just waiting for that one single node to process, right? So that's huge for consuming a lot of compute and creating a lot of idle time on the other instances. And then another wastage pattern you'll often see on data processing frameworks is partial or failed executions. So imagine you ran a sort of data pipeline that runs for 10 hours and eventually fails at the last node. The whole pipeline is useless, right? So the data, most of the time, you cannot replicate or rerun from partial executions. So that is a huge issue. The next thing is often computation. So this is normally a byproduct of platformization. So you have a UI layer that gives you access to the backend. So you run your query. Query gets executed in the backend. Your client gets disconnected, doesn't know whether the query is running. And then what that creates is this often computation in the background, which keeps running, consumes compute, and you don't even know whether it's processing. And it can also cause another side effect where you can query another time, and it's going to create duplicates for you. And last, one of the sort of crucial aspects is having access to distributed database processing or distributed data processing. Sometimes you have these anti-patterns where you mix IO-bound with CPU-bound work, and these IO-bound processes become your sort of bottlenecks. They reduce how fast your pipeline executes and finishes. So at the end of the day, it leads to underutilized compute because a lot of nodes that are waiting for one particular task to finish. Then you have excessive idle time, again, a lot of wastage. Repeated tasks because of partial or failed executions. And then you have over-provisioning because you want to scale your IO-bound tasks, so you just run with more instances. And you barely use the CPU for it. And lastly, you end up with a lot of dangling temporary assets. So if your pipeline fails, you end up with artifacts that you have to go in and manually clean up. And these can remain forever in your storage unit. So be careful about these. And when you think about remedies for these, you think about implementing custom checkpoints in your batch pipelines. What that means is materialized stages, which are really computationally sort of expensive for you, or you're relying on external services to get that data. The other thing you can do is you can combine that with delta tracking. So what that means is programmatically, when you define your data pipelines, you make sure that whenever you repeat or rerun the pipeline, you don't have to change anything. Everything is built into these queries which track for delta at each step. And whatever the pending execution that needs to be made, that's the only step that you execute. So complete input minus partial data, delta tracking. Next is implement custom data loaders for page reading from tables. So if we go back to my reference around combining IO-bound with compute, what ends up happening is you have a lot of computes which are scanning very little data and processing it sequentially, right? So what you can do is you can amplify that by reducing it to one single node implementation where you can have async API executors, which looks something like this, right? So you have the data, and then you have the custom loader that paginates your reading from the table, and you read it into a single instance which does all your async calls for you. So this drastically reduces your compute costs. I've been able to leverage these patterns to, at times, reduce the cost of reruns close to about 90%, right? So it's a huge saving if you start implementing these patterns because these are not natively available in most of the frameworks. Next suspect, we're talking about the GPU, right? Beautiful beast, very powerful for ML inferences. Very few understand them well, and at least underutilized, and it leads to very underutilized instances. And most of the time, it's an artifact from misconfigured execution, right? So people not understanding how VRAMs work, right? Not having proper compatible drivers installed with the toolkit that you have in your image, right? Or having implementations which use fast API service wrappers to run your inferences. So what that does is it's a lot of wasted compute, especially with GPUs, because it's super expensive, and everyone's using them. And Jensen wants them to be bought by everyone, so yeah. So the remedies for this is automate the shutdowns, have monitors that are custom for GPU memory utilization, right? That give you insight immediately that whether you're actually consuming your GPUs that you have sort of provisioned. Next thing is optimize GPU inference with proprietary inference servers, right? So use Triton, dedicated servers which are there to host your models that can support multi-instance deployments. What this does is when you have a GPU which is, say, 16 gigs of memory, you're not deploying a model which is barely a GB, right? And using that. You can deploy multiple instances of those 1 GB models and stack them up and have higher throughput. So that reduces your requirements for more instances. The other thing is server-side batching. This is huge. This is one of the big sort of impactful features in inference servers. What it does is rather than batching on the client side, the clients can make individual calls. In the back end, the server will combine these calls into a single execution for the model, and you run the inference and return that back. So this makes it highly efficient for you, right? So remember to use this. And yeah, so lastly, we come to the external API log and egress. They often work together in groups, highly notorious. You least expect them to be causing you issues. But again, a lot of chatty services, a lot of logs, incorrect log levels lead to this. External API calls which are happening over the internet, they'll cause a lot of egress, right? And then cross-regional, cross-availability, zone transfer networking costs, right? So not a lot of people think about it, no such thing as too much logging. But again, ask these guys who just spend 100K on just logging, right? So yeah, remedies, understand your logging services, ensure proper log levels, proper structured logs that can make it easy for searchability. And lastly, implement log segregation, avoid cross-region service calls. And yeah, if you're working across clouds, you can use VPC peering. So with that, we've come to the last stop of this journey. I hope that helped you guys in having a more sort of cost-efficient path forward. With that, thank you very much.